So, all right, you guys can do this exercise actually on yourselves using the same method I just explained. And yeah, try to find both the partial derivatives to s and then with respect to s and then with respect to t. If you're done, either lift your head up or give me a thumbs up. That would be very helpful. If anyone has any question, you can also send me a private chat if you want to. All right, I can see that a few people are good to go, so we'll go ahead and talk everyone through it. So, all right, when taking the partial derivative with respect to s, what we'll do again is treat every t as a constant. So this natural logarithm of f squared using this formula that we saw during the last workshop, we'll see that it becomes 2s over s squared. Because we're differentiating with respect to x, this element here then becomes 0 and is not included in the next step. And this element becomes minus 4 over 7 s minus 3 to the power of minus 3 to the 7th, or 3 over 7, sorry. If you simplify this, you get this. Here again, the partial derivative with respect to t will therefore not consider this argument, or will consider it, but because it is a constant, it becomes 0. For the rest, the natural logarithm of s squared is treated as a constant again and is not differentiated, but the t to the 7th will be, and the 7 comes forward, decrease the power by 1, and the same thing here for 9t to the minus 3, sorry. Cool. All right, so moving on, an interesting topic that does come forward from time to time within econ is the higher derivatives. So some type of double derivative. So what the first derivative here represents is a double derivative with respect to x. So what we'll do in order to compute this will be take a normal partial derivative with respect to x and then do the same thing again. Where it gets somewhat more interesting, it's when we differentiate with respect to x and then y, or y and x. And here again, it's the same thing where we differentiate twice with respect to y. I'm also wanted to introduce you guys to this whole notation and maybe this one too, as could seem quite confusing initially, but it simply represents a double partial differential. Please note that the later differential that is taken is on the left here. Is something that you might see coming by quite a few times. It's important to remember. Cool. All right, so now talking about multivariate optimization. Mathematical optimization is the process of maximizing or minimizing an objective function by finding the best available values across a set of inputs. So the objective function will often be expressed in terms of f. So this, for example, is an objective function. What this helps us to do in economic terms is if we're talking about utility or production, we'll try to find the best set of available inputs in order to maximize our profit or utility overall. So this will be quite relevant, and I think is the most important part of this workshop for you guys. One thing that's very important to remember is that those maximum and minimum happen when the partial derivative are both equal to 0. That this will be the technique kind of that we'll be using in order to find those maximum and minimum, is that we'll take partial derivatives of our function, set those equal to 0, and then work our way back to those values of a and b. All right, so an example, we'll do a few more of those. So the way we'll approach this, as I said, is by taking a partial derivative. We'll first take a partial derivative with respect to x, which ends up being 2x. We ignore this because we treat it as a constant, minus 2. Ignore this because those are constants again. Same thing with y, 2y minus 6. We ignore the rest because we treat them as constants. All right. Therefore, the point where we maximize those, I kind of jumped a step here, I'm sorry. Are going to be x equals 1 and y equals 3 because we set those partial derivatives to 0. So we can then add 2 to both sides, and then divide by 2 on both sides, which gives us x equals 1 and then y equals 3. The way we can kind of verify whether our answer is good or wrong is by putting in a few other inputs. So we see that the value of our function at 1, 3 is equal to 4. And then the value as other points is always larger. You can keep going with the number of different inputs that you want, and you will always see that 4 remains the smallest one. Hence, the value f(1,3) is an absolute minimum. Does that make sense to everyone? Real good? I'll take that as a yes. If anyone has any question, please don't hesitate to interrupt me. Like raise your hand or send something in the chat. All right. Oh, actually, sorry. I just noticed there were a few messages in the chat. I don't really get the notifications apparently, which is unfortunate. Okay, I saw the problem was solved. All good. Cool. All right. So constraint optimization is the process of optimizing again an objective function, which is always the first argument in those type of notations, with respect to a constraint on its variables. So the constraint in those variables here is represented by this second part. ST means subject to the constraint. Here we can see that this is a typical example of a utility maximization problem that you guys will see in Econ 250 or possibly later on. And yeah, here is more of a mathematical version of the problem, which is supposed to represent trouble here. Yeah, which is supposed to represent the volume of a box without a lid. So if you count all those up, they're supposed to represent all the sides. And yeah, this is not that applicable to economics, but still an interesting maximization problem if you guys want to have a go at something maybe a bit different than economic maximization. Cool. All right, so there's two different techniques that I personally use when it comes to multivariates and constraint optimization. The first one being the Lagrange technique. So understand that this is a bit wordy, but we'll look at examples right after this, which should make it somewhat clearer. The way the Lagrange technique works is by adding an element to the objective function to account for the constraint in its arguments. So what we'll do is take all arguments and put them to one side of the equation, and then set that to 0, which will later on add to the objective function. We can do this because the sum of all our arguments or all elements, if we put 16 on the right-hand side, is equal to 0. We'll then look at all the different partial differential with respect to all variables, so those being C in this case, L in this case, and the Lagrange multiplier, which we will see later on, which is represented by a lambda, I believe. I think it's a lambda. Yeah. So what this will help us do is to directly integrate the constraint within our optimization problem, which should result in the critical points of our function coming up with respect to that constraint. All right, now looking at an example, I think it should make it a bit clearer. So what we're trying to do here is maximize our utility given those possible sets of inputs. So X and Y in this case will often represent two different goods. But as a customer, you'll be subject to a certain disposable income or time or whatever the limit is that you're constrained with. So what we'll try to find here is the optimal X and Y so that your utility is maximized. The way we go about it is by, as I said, rearranging this side of the equation to make it equal to 0. So here 2x plus y minus 10 equals 0. I hope we will see that. Again, if you guys have any questions or if anything is unclear at some point, don't hesitate to tell me or to stop me. Cool. So we've directly introduced this constraint into our function. Here I would just make a quick note. I've realized that I made a typo. U should often not be, here you shouldn't use U, you should use this type of L. I'll quickly maybe annotate it here. Sorry if it's terrible writing, but this type of L is often used within economics because yeah, it's just a general agreed upon notation that actually refers to the Lagrange function or the Lagrange technique overall. So I see a question from Loïc in the chat. When should it be minus lambda vs adding lambda? It can be whatever you want. The only reason that here I use minus lambda, actually it'll become clear later on. I'll point it out when it does become clear. So what we'll do here, the next steps is to take the partial derivatives with respect to every different input or variable, those being x, y, and lambda. So with respect to x, I'm sorry, this x should be here. But yeah, with respect to x, we'll we'll divide by 4 because we're multiplying by 0.25 and then subtracting 1 from 0.25. This will be rewritten like this because if a degree is negative, we can divide by the positive degree. If that makes sense. We'll then do the same thing with respect to y. I'm very sorry. Again, it shouldn't be an x here. It should be a small y at the bottom. Here we'll multiply by 3 over 4 because that's what 0.75 is. We multiply by 0.25 over 4. And we take 1 away from the degree of our y variable. I hope maybe this part makes sense as well. I kind of skipped a step. So here what we would do if you want to write it the full way is we'll distribute lambda across our brackets. So it'll become minus 2 lambda x minus lambda y plus 10 lambda. So what we end up here is those two variables, or those two partial differentials. And then last one, here I got the notation correct at the beginning. But that's what we, actually that might be wrong, but yeah. In this case, it doesn't matter because if you put all variables to the other side of the equation, you get what it should be. So it's just a question of rearranging. I hope that kind of makes sense. But yeah, this should be minus 2x minus y plus 10. All right, so Loïc, here is where I answer your question. Here we go. So what we're interested in doing is finding the intersection points, so finding the x and the y where all those partial differentials are equal to 0. So what we'll do in order to find those is set up a system of equations and find those equilibrium points, or not really equilibrium points, find those intersections, we'll say. So the reason I chose minus is because it's maybe a bit easier to to figure out, because if here was a plus, then it would be minus lambda, and then you had to divide by -1, and then you'd have a negative term over here. Just that using a minus here enables you to have a plus here, which just makes it a bit simpler. So we'll rearrange our functions like this, and then equate both functions in order to find the point of intersection. The point of intersection here, because if you distribute the power across the bracket, you get x to the 0.25, y to 0.25, y to 0.75, x to 0.75. And if you multiply, let's say, both sides by x to the 75, you'll end up with x to the power of 1 here, which is represented by this. I hope that kind of makes sense. And same thing, if we multiply by y to the 0.25, we'll get y to the power of 1. What I also did is multiply the whole equation by 2, which gives us y equals 6x overall. Cool. So now, using the last part of our equation to make sure that our function follows every single partial derivative, we'll put 6x instead of y into this equation, which gives 2x plus 6x equals 10, which gives us our first value for x. And then we'll do the same thing. Oh, I'm sorry, your cameras ended up hiding this on my screen. But yeah, which will enable us to then figure out the value for y. What I did here, again, I should have added a step, which is that I plot the 5x, which is 5 over 4, sorry. X equals 5 over 4 into this equation, which gives y equals 30 over 4, which is 7.5. Cool. Does that make sense to everyone? Are we all good? Any questions? One more thing that I would like to note for you guys is that those three equations are called the first ordered conditions. So the partial derivatives, the three partial derivatives within the Lagrangian techniques are called first order conditions, FOC, which your teachers might point towards within Econ 250. Cool. Now, quickly clear my notation. And we can move on to the next slide. All right. So the substitution technique, I believe, or actually no, yeah, the substitution technique is somewhat easier when it comes to functions of only two independent variables. It makes you have to do somewhat less calculations, but the calculations might be a bit more difficult because often they involve the product rule, which is a tad more complicated than what we did in the previous exercise, I think. What I would recommend doing is try to get as used to as possible to the Lagrangian technique, because it's very applicable to, even if you get to like functions that have more independent variables than 2, if you get to 4D functions or functions with 3 independent variables, this technique is as useful, where the substitution technique might then become a bit more complicated. See that there's will the PowerPoint be posted? Yes, actually it will. It will be posted on the ESA website, which should come soon. I think it'll be posted by the end of the week, as well as the recording of this tutorial. We'll make an announcement on Facebook. as well about that. All right, going back to the substitution technique. Going back to the substitution technique, what we'll do here, instead of directly, instead of adding another element, we'll actually substitute an element within our objective function. So yeah, actually I'll directly go to the example. I think it's probably the most useful when it comes to this. All right. Wasn't just supposed to show everything at once, but it's fine. My effects didn't work out, unfortunately. So what we'll do is rearrange, like the way you start your substitution technique is by rearranging the constraint like this. And this enables us then to change our utility function or our objective function to this, as we just substituted y by 10 minus 2x. What we'll do then is a normal partial derivative like we did earlier, where we'll just take a partial derivative with respect to x and then set that one to 0 in order to find the values of x that satisfy this equation. So can maybe quickly walk you guys through the calculations, but it's pretty much the same as we did before. The only the only thing that changes is that here we'll have to use the product rule, which does somewhat complicate things. We have to use a product rule because actually we don't have to use a product rule now that I think about it. Oh, actually I wasn't smart. I didn't do it. I didn't do this the right way. Could have just distributed for x. Actually, no. I'm sorry. All right, so no, we do have to use a product rule because there's a power of 0.75 here, so we can't distribute the x over. So what we'll have to do here is take the derivative of the first part of the function and multiply it by the second part of the function, which we do here. And then we'll have to do it the opposite way around. So take the derivative of the second part of the function and multiply it with the first part of the function. This is the derivative of the second part of the function. There's also something interesting going on here, and that's the chain rule, is that we need to multiply the derivative within the function with the derivative from, or the coefficients that come through from the derivative within the function with the coefficients from the derivative of the function from outside the brackets. I hope you guys remember that, and I hope this is somewhat clear. I should probably have added it here, but this is part of the chain rule. All right, if you end up simplifying all of those, you get to this. And by adding 6x to a quarter times 10 minus 2x to minus quarter to both sides, you get this equation, which then enables you to simplify those, simplify it to this by multiplying by x to the minus 3/4. My pointer was broken for a second, sorry. Which, yeah, overall simplifies to this, and which gives us the same answer as the Lagrangian. Cool. All right, so now I would like you guys to have a go at this using the Lagrangian method that we discussed earlier on. If you guys want, you can copy this equation, and I'll go back a few slides in order to kind of show you the steps. The answers. To kind of show you the steps of how exactly we went about it in like 5 minutes or 3 slides ago. I'll assume that everyone now has the problem and the constraint, and I'll leave you potentially with this slide, which should help. Let me know when you guys are done. Again, if anyone wants a clarification question, a clarifying question, sorry, don't hesitate. I'll be back in a second, sorry. All right, I'll leave you guys 1 more minute to work on this, and after that we'll start discussing. Don't worry if you're not done. All right, go back to the exercise. Maya, I don't know if I understood your question right. I'm a bit confused as what exactly you were asking. But what we're initially trying to do, solve this. The reason I showed the other slide, the previous slide, was to just give you a general way to go about it. We'll give you somewhat of an example to follow, but this was initially what we're looking for. All right. So we'll go ahead and discuss how you can use the Lagrange technique to solve this problem. So what we did here again is by integrating the constraint within our objective function by setting this equation to 0 and then multiplying it with the Lagrange multiplier by putting the 100 on the other side. You get this. All right. So now looking at our first order conditions, again, we'll have 3, one with respect to L, one with respect to K, and one with respect to lambda. In this case, try to, when you're writing your this L, try to write it that way so you can make a difference between this L here And I don't know if you still see my pointer, sorry. But yeah, so you can make a difference between this L here and that L. So look at our first order conditions. We'll get the first one, which is with respect to labor. So we get this derivative, which is 20 times 0.8. And then we take one of the 0.8. And we'll do the same thing here. So by multiplying it out and then taking the derivative, we get 2 lambda, because L is to the power of 1. Moving on to the second first order condition, we get 20 times 0.2 L over K degree of 8 minus lambda. Again, the same logic applies. Does that make sense to everyone? Does this way of finding the first order variable in order to set those equal to 0 and find a maximizing point somewhat make sense? Hope it does. If something's very unclear, let me know in the chat. So the third first order condition would then be the derivative with respect to lambda. So we get 2L plus K minus 100, which again is wrong, but it actually doesn't matter. But yeah, it's wrong. It should be negative here, plus here. So we'll now set the two first order conditions equal to each other. I did somewhat skip a step over here. I hope that's kind of clear for people, because the 2y now goes to the opposite side if this is 0, so we divide by 2, and 20 times 0.8 is 16, so 16 divided by 2 times k over L to the power of 0.2. The second right-hand part to this equation comes from the second first order condition, which is 20 times 0.2, which is 4 times L over K to the 0.8. Again, I hope this is clear that we got this by adding lambda to both sides. So it's as if we didn't have this. Sorry, my pointer is a bit broken right now. I don't exactly know why. It's as if we didn't have this this element, but that we did have a lambda here. And again, that we didn't have this element, but we have a 2 lambda, or a lambda once we divide it by 2. So this is the same equation. I'm not exactly sure why I included it twice. But what we do end up having is, so 8 here, so 8 divided by 4, which is 2. After multiplying by k to the 0.8, we get k to the power of 1 on the left. And after multiplying both sides, I want to talk about multiplying is naturally both sides, otherwise it's not a valid equation. We do get L to the power of 1 on the right-hand side. So we would obtain 2k equals L. Now using our last first order condition, we'll plug this value of L here, which is 2k, into the last one. If I didn't do the opposite, yeah, that's what I did. So it would have been 2, sorry for again making a shortcut here, but it would have been 2 times 2L, 2 times 2k, sorry, which is 4k plus k, which ends up being 5k. And if 5k equals to 100, k then equals 20. Using this equation, again, k equals 20, so L equals 40. All right. This is quite intricate, and it will take you probably some time to get used to it. If you've already nailed it on the first time here, then good for you. Your first year is probably going to be a bit easier. But yeah, try to really nail this and understand really how the overall Lagrange technique works. It's something that's definitely going to come up on probably your midterm and your exams. I'm not exactly sure about your midterm, but I'm pretty sure about both of your exams. I'll quickly take the drawing out. All right. So now moving on to double integrals. This is, yeah, please remember that this is somewhat of a stretch. It's only partially covered in Econ 250 and is not that common either. So the way double integrals work, or the way I see them, is by understanding that we take the integral under a function and over a plane. But when talking about this function, we're talking about a surface or an area, or yeah, a surface or an area, which is something that exists in 3 dimensions. Hence, we'll end up with a volume by integrating all parts under that surface. I hope these little drawings somewhat helps you to conceptualize what exactly I'm talking about. But yeah, that's kind of it. So the way we'll compute integrals is by first integrating with respect to x and then with respect to y. I put this here because I would like you to remember that it doesn't really matter which way you integrate first. Yeah. Or at least with those type of examples which have definite limits, a clear start and end, it does not really matter which is started first. All right, so as I said, the way we'll go about computing those integrals is by first computing the integral or the inner integral with respect to y or whatever variable is within the inner integral, and then take the integral with respect to the outside integral, or the second variable, which in this case is x. So to give you an example, again, here we'll integrate this function with respect to y, and then with respect to x, we'll treat x as a constant in the same way that we did with partial derivatives. So this integral, as we've seen last lesson, with respect to y, gives 2x y to the third. This bar here represents the fact that we need to plug in those values in order to get the overall value for the definite integral, which was previously used outside of the integral, but the same notation applies whether or not it's inside or outside the integral. I hope that makes sense. So by plugging in the values, we get 2 to the third, which is 8 times 2, 16x, minus 2 times 1 to the third, which is 2x, ends up giving 14x. Moving on at that point, we'll integrate this one again, just like a simple integral, as we did for the inner integral here. Which will give us this as we're raised by 1 power, so you add 1 to the power of x, and then we divide by that new degree of the power, which in this case is 2. 14 divided by 2 gives 7x squared. Plug in those values, and you get 84. Cool. All right, so this is, I believe, the last slide of our presentation and of our workshop. It's just a quick exercise for you guys. I think the values get quite big. Yeah, I don't want to show the answer, but I think they do, so don't hesitate to use a calculator. All calculators are, I think, about in exams, at least for econ 215, econ 230. So you would be able to use this in an exam too. Yes, Stephanie, you can swap the integrals placement. As we saw here, I'm talking about definite boundaries. You can, or not as we saw here, sorry, as we saw. All right, we'll go ahead and start having a look at it. Don't worry if you're not done again. It's not an easy topic. The more you practice, the faster you'll become. So I think you should be all right. Cool. So the way it works again is that we'll treat all the x's as constants and all the y's as variables when integrating with respect to y. So this first term should become 2xy. The second term should become minus y to the power 4. The reason this happens is because we raise to 1 power. Let's say the polynomial rule for integration. Raise by 1 power and divide by, we raise the power by a degree of 1 and then divide by that new degree, which we did here. So, but after plugging in the values, it's 6x and that's minus 81. Yes, 27 times 3, 81. Again, here we'll do the same thing. It ends up being a simple integral. So this should become 3x squared minus 81x. We'll then plug in the values, which gives minus 756. All right. I believe that this is it for the slides. And this is it for the workshop. If you guys have any questions, now's the time. All right. If no one has any questions, I'll